should I start, or is it recording?
Yeah, go ahead. Yeah.
Okay, so I don't see it recording, but I guess I can't see it. Never mind. So this is work which we just put out recently, and I'll jump right into it. So this is done in collaboration with Anisha Chandran and Chris Lawman at BU. So before I jump into the talk, let me give you the summary to give you the upshot right here. So let's look at this picture over here. So this looks like a typical phase diagram. It looks like there's a tuning parameter phi, and there are different parts of the phase diagram. This green phase here, this blue phase here, and separated by this critical point over here, each of which has different spectra. But the interesting thing here is that such analogous structure can occur in a completely different setting, where you have, so these actually here are entanglement spectra of constraint systems, so of typical states in constraint systems. So if you take a high energy excited state in a constraint system and you look at the entanglement spectra, and if you tune the constraint in some way, which I will talk about later, the entanglement spectra undergo phase transitions with different phases being characterized by the singularity of the spectra near origin. So you can see that this phase has a square root singularity at origin. This phase is gapped at origin, and they're separated by a critical point with a 2/3 singularity near the origin. So there really is some interesting structure in the entanglement spectra and constraint system, and they're universal in some sense, which I will come to later. And
can I ask already a
sure.
question here? So an unconstrained system, is that then the black mark, the blue marker in the gap?
So I'm in this whole talk, the formalism is general, but in this talk I will focus on bipartite entanglement entropy with a balanced cut. So it's exactly a half cut. So this gapped part, the fact that this is gapped does not come because of the usual choosing an unbalanced cut. So the unconstrained case would be somewhere way out here. So most unconstrained systems would be in the so-called MP phase, which is the Marchenko-Pastur phase, which I'll come to. So most ergodic eigenstates of ergodic systems and unconstrained systems will have a square root divergence at origin. Yeah.
Okay.
Right. So now that the key message is out, so I'll give you an outline. So what is the motivation for this whole work? Why constraint systems, and what does entanglement look like in typical or generic eigenstates? And then how do you actually parametrize constraint spaces in a general way? And then I'll come to some formalism to actually calculate things, to calculate the entanglement spectra. And then I'll talk about what an entanglement phase is, and what sort of critical exponents and phase diagram do you have, and why is it actually universal, or what sorts of universality do we mean here? And I'll show some numerical benchmarks and actual model systems which bear out the calculations and intuition so far. So on a high level perspective, constrained Hilbert spaces are really abundant in physics. The simplest sets of constraints are global symmetries. So you can have magnetization, SU2. So you can have any sort of global symmetry, and that would be a constraint on a system. But another sort of constraint is a local constraint, which is where a lot of the interesting physics in this talk comes about. So what do we mean by local constraints? So local constraints occur in a wide class of systems. So the most prominent of which are gauge theories, but in condensed matter, you also have frustrated magnets, like dimer models where dimers do not touch each other, or you can have spin ice where you have a local constraint of a 2-in, 2-out ice rule, or you can also have chains of Rydberg atoms where interactions means that where a specific mechanism of Rydberg-blockaded introduces a local constraint into the system, and I will get to this more in the next few slides, because this will serve as a running example for the calculations we do. So now the Rydberg-blockaded atoms are a nice example, because the Hilbert space realized by Rydberg-blockaded atoms and encompass a wide class of systems. So you can have anion chains, spin chains of anions. You can have dimer ladders. All of these have the same structure of the Hilbert space in that there is, it is a two-level system. So you think of a chain, and you can have two-level systems sitting on each side of the chain. And the only constraint you have is that you do not allow for up and up on neighboring sides. So that's the Hilbert space, which encompasses all of these systems. The Hamiltonian might be different, but the Hilbert space is exactly the same. It's this constrained Hilbert, it's effective constrained Hilbert space where you do not allow up and up on neighboring sides. And so now to give some motivation, now let's look at Rydberg atoms. So why this is a constrained system? So this harks back to stuff about 2 decades ago, but which was really brought to a head through experiments in the last 3 years, where neutral rubidium atoms were held in a lattice by optical tweezers. And the interesting thing is so you can think of these atoms are just as two-level systems, but now they have strong van der Waals repulsion between them, which means that it is the state when both of them are up and up is very high in energy. So for all practical purposes, that state is completely projected out of your Hilbert space. So this n is a very large quantum number. It's a principal quantum number, which is large, and it's to the power of 11. So this value is pretty large. So these states are just completely projected out of your Hilbert space. And so you can effectively think of your Hilbert space as having no consecutive up and up. And this is a pretty strong constraint given the energy scales. Now you can ask, what does this constraint actually? So why is this constraint interesting? It's useful. It's interesting to see that there's a constraint, but why? What are the implications of it? So one prominent implication, which was seen 3 years ago, was that there was unusual when people did quenches on a Rydberg-blockaded chain. They found unusual dynamics. So what they were looking at here was they started with a state which is essentially an antiferromagnetic state. So you started the chain with this up, down, up, down, up, down state. And then you act on it with a Hamiltonian, which is just a transverse field. So if it was now for the Hamiltonian, which is just the transverse field, the state which is up, down, up, down, up, down is very high in energy. It literally lies in the middle of the spectrum. So it's an extremely high energy state. So the naive expectation would have been that you just expected to thermalize in a sort of boring way. But what they found was much more interesting, that they found these long-lived oscillations which persisted in the system. And the reason for that really is that there is a strong constraint in the system, that these van der Waals interactions means that there's an effective Rydberg blockade in this system. So just to illustrate this so this is the experimental data on the left with an appropriate order parameter which shows oscillations. So on the right, you can see that if you change the this is numerical data. If you change the van der Waals interactions to a nearest neighbor blockade, the oscillations become even more long-lived. So they become even more prominent. Just to illustrate that the constraints really here are playing an important role. The Hamiltonian is sort of boring. The initial state is also trivial. It's not a highly entangled state. It's just a product state. But even with these simple ingredients, once you add a strong constraint into the system, you can have unusual dynamics here. And now this was this experiment on its own has led to a huge field. And so this will be my one slide where I will break convention and not talk too much about what is being plotted here. But I just want to illustrate that if you take constraint systems, you can have this. This has given rise to a lot of new ideas and directions just from the fact that you have, just from the simple constraint. It's not a very complicated constraint. It's a very simple constraint. But you can have generalizations of many body localized phases and ETH phases. So you can have constrained thermal phases and constrained MEL phases. So so these are all finite temperature, so that very high up in the spectrum. And then what you're seeing here is that if you add additional perturbations, U and V are sort of like Ising interactions, different range Ising interactions, which are projected down into the blockaded space. Then you have unusual phase diagrams. So when you don't have any additional interactions, this led to the so-called discovery of the so-called quantum many body scars. And at certain points, you have integrable regions in the phase diagram. So all I want you to take away from this is that even if the Hamiltonian is boring, even if your initial state is boring, if everything else is boring, just the fact that you have constraints can give you a lot of interesting physics, even for excited states. So remember, here we are looking at states right in the middle of the spectrum. You started with a state which is not a ground state. You've started with a state which is high, somewhere in the middle of the spectrum. And people thought they knew a lot about these states. But clearly, once you add constraints, that this gives you a lot of new physics, even for states right in the middle of the spectrum. Right. So this brings us to the question in this talk. So what is the structure of entanglement of typical states in isolated constraint systems? Because entanglement has proven a very valuable angle to understand both dynamics and why many body systems are interesting, why some many body systems are interesting, and why others are sort of trivial. So entanglement has provided a very useful metric to understand this. So it's a natural question to ask, what is the structure of entanglement of the states in these constraint systems? Now, again, we're talking about typical states. So these are states in the middle of the spectrum, which were usually thought to be sort of well understood. They have volume law entanglement, and they have something called a Marchenko-Pastur law in the entanglement spectrum, which I'll come to. But clearly in constraint systems, something else can happen, and that's what this talk aims to show. So let's take a small detour. How do we actually study the structure of entanglement in any isolated system? So broadly, there are two aspects to it. It depends on what quantity you measure, because there are a plethora of quantities you can measure, and what is the structure of your wave function, because you're really asking about pure states, and you're asking what is the structure of your wave function. Is it a completely random wave function? Does it have structure to it? So it depends on these two quantities. So let's look at what quantities to measure. So and this detour might seem elementary to some, but it will help with notation. So please bear with me. So how do we quantify entanglement in a wave function? So imagine you have a system. This blue box here is just in some isolated system. And now you divide the system into two parts, A and B. So, and you want to ask about what is the bipartite entanglement between this subsystem A and subsystem B. So you want to ask how entangled are these two parts of the system with each other. Now you can calculate a density matrix. So you're assuming, so you have a pure state and you have a wave function. So you can calculate density matrix from which you can trace out one part of the subsystem. You get a reduced density matrix. And then you can calculate a single number, which is the entanglement entropy. So the one Neumann entanglement entropy. And if this number, so this number essentially tells you how entangled these two parts of the system are with each other. Entanglement of 0 would say that they're unentangled, and the non-zero value would typically tell you that there is some entanglement between them. But now this is just a single number, but much more general is the full spectrum of the reduced density matrix. You could call this the entanglement spectrum. It has been used in a slightly different notion in the context of ground states in the last 10 years, which I will come to later. But for the purposes of this talk, all I mean by an entanglement spectrum is that it is a full spectrum of the reduced density matrix. And now if you look at bipartite entanglement, the spectrum of rho A contains all the information you'd need. There's nothing more general. This is the most invariant thing you can look at in the system, subject to local unitary transformations on both A and B, which is still invariant. And so this is, if you have the spectrum of rho A, you can calculate any other quantity in bipartite entanglement. So now to illustrate, now to set some notation, let's look at a two-spin system. Let's just imagine you have exactly two spins, A and B. And now if you have a Bell state, and now I can write it as a row vector. So 0, 1, 1, 0. But instead of writing it as a row vector, I can write it also as a matrix. So where the rows are the right, so the columns are given, but indicate the B subsystem and the rows indicate the A subsystem. So this matrix has two indices, I and alpha. So throughout this talk, I will use I to denote the A subsystem. I will use Latin indices to denote the A subsystem and Greek indices to denote the B subsystem. So here I goes from 0 to 1 and alpha goes from 0 to 1. And then now the useful part of writing it as a matrix structure is that you can shortcut the calculation of the reduced density matrix. So you can, by just doing matrix multiplication, taking the psi dagger will give you the reduced density matrix, because you're tracing over the intermediate, over the B subspace. So for this example, this is the reduced density matrix. You get an entanglement entropy of log 2, and you can look at but you can also look at the entanglement spectrum. So it has two eigenvalues of half. So this is like weight 1 so it's a delta functions with weight at half. Now you can ask what happens if you have a state which is unentangled. So this is typically an unentangled state. So you can go through the same behavior, and then you see that again your entanglement entropy is 0, telling you that your state is unentangled. But your reduced density matrix also has some interesting information that the entanglement spectrum is different between these two cases. This is a trivial example where the entanglement spectrum hasn't told you anything more than calculating the entanglement entropy. But once you actually put in a thermodynamic system, the entanglement spectrum does have more information than just a simple number, which tells you how entangled state is. So now one thing I want you to take notice here is that all of the structure is in this matrix. How entangled the system is, how unentangled it is, any constraint structure, any structure of the Hilbert space and the wave function should be in this matrix. So it is really by understanding how do we put in constraint structure into this matrix and then calculating things with it, will we have a handle on the things we want to calculate. So now, as I've said before, just now, entanglement properties depend crucially on the structure of the wave function. So now let's ask what is the structure of the wave function? So let's ask what is the structure of an eigenstate? So you can decompose a state into its basis states, and now all of the structure is in here. Now, if you go to 0 temperature, there's a spectrum, but you'll be only in the ground state. And the ground state is can have very interesting structure. So you can have a ferromagnet, antiferromagnet. You can have something more exotic, like a equal weighted superposition of loops, like an toric chord state. You can have a fractional quantum Hall state. So all of these are highly structured states which occur at, when you're looking at ground states. So ground states have a lot of structure in them. But and now just to hark back to the entanglement spectrum, Lee and Haldane did look at essentially taking a logarithm of the definition we've looked at so far, but looking at the spectrum of the reduced density matrix for wave function, the fractional quantum Hall effect, and they found that there are you can infer very interesting things just by looking at the entanglement spectrum, which you could not do by looking at the entanglement entropy. So calculating the spectrum of reduced density matrix is quite old, but calculating it in a physical context for ground state wave functions was first done about 12 years ago by Lee and Haldane. Now,
Sid, can I ask a question about this? So I thought you said that capital A is an eigenstate of some local Hamiltonian, correct?
Capital. Sorry.
Capital A is the composition.
Oh, so.
No. Or
So sorry. I'm sorry. I should have talked about notation. A are just basis states. So psi is eigenstate. A is just basis state. So you choose whatever basis you want. In many bases, psi will have a nice specific structure. It's a matrix, yes, but the matrix is usually has a very nice structure, and it'll be typically a sparse matrix. But now if you go to let's say go to infinite temperature. So infinite temperature means somewhere in the middle of the spectrum. So you're choosing some state in the middle of the spectrum. You can ask, what is the structure of your eigenstate? And none of this applies. So you can ask what happens. And the answer to this goes back a few decades ago. So originally conjectured by Berry, it's called Berry's conjecture, and formalized in the eigenstate thermalization hypothesis, which says that to a good degree of approximation, these matrix elements are totally random. And so the ETH tells you much more than this statement, but for our purposes, this is what we need to take away, that in an ergodic system, if you're looking at some state in the middle of the spectrum, these coefficients are totally random. So that tells you that random wave functions can be interesting. It might be useful to study random wave functions. So let's ask, what is the entanglement structure of a random wave function? Remember, we're looking at entanglement spectrum because that's the most general thing we want to calculate. So what is the entanglement spectrum of a random pure state? So now your psi is literally a random matrix. All these elements are Gaussian random this is a Gaussian random matrix. And now you can calculate your rho as psi dagger, and this is called a V-shot matrix. And once you take the thermodynamic limit, your spectrum becomes a spectral density, and the spectral density gives you something called the Marchenko-Pastur law, which I'll plot here for you. So the Marchenko and Pastur derived it many decades ago in a different context. But this is what you get for a matrix of this form. You get a Marchenko-Pastur law. And the main thing I want you to take away from this law, so it's some spectral density. That's nice, but the thing I want you to take away from this is that there is a square root divergence at origin in the Marchenko-Pastur law. So if you take a wave function which is a random matrix like this, you get a square root divergence at origin. So now how applicable is this to actual eigenstates of physical systems? So there is evidence that the square root singularity is actually robust. So there's a numerical evidence a few years ago. So they were looking at a disordered Heisenberg model, and this model here it's a 1D disordered Heisenberg model, which has a transition from an ETH phase to an MBL phase, where of H around 3.5, and so what they were looking at is what happens to the entanglement spectrum when you look at different points in the phase diagram. So H equal to 6 is in the localized phase. So I want you to ignore this last panel here and concentrate on these other 5 panels. These 5 panels are eigenstates of this, are highly excited, as the entanglement spectrum of highly excited eigenstates at different points in the ergodic phase. And you can see that, and the red line here is the Marchenko-Pastur law. So they've plotted it, this graph is flipped compared to the previous graph by 90 degrees. So the x-axis is the Schmidt values and the y-axis is the probability density. And this is there's a logarithm here. So it's slightly shifted. For convenience, there is a Marchenko-Pastur law in each of these panels, which is this red line. And you can see that at small h, it seems to agree. The Marchenko-Pastur law does describe your entanglement spectrum very well, but then there starts to be deviations. But if you only focus on the low energy part of this entanglement spectrum, you can see that always seems to agree. So the rest of the entanglement spectrum might change, but it seems like the low energy part seems to be more robust, and the square root singularity seems to be a robust feature. So that tells us that ergodic systems, this might be one universal aspect of ergodic systems, in that the square root singularity tells you that you're in the ETH phase and you're in excited eigenstate of ETH phase. But then how valid is this in constraint systems? Does this continue to hold in constraint systems? And as we will show, this can actually change in constraint systems. So as an aside, I want to talk about a question which was asked about 3 decades ago. Is it possible to ever figure out you're in a random pure state? So let's assume the universe is an isolated system, and you want to figure out if you're in a pure state and you're governed by some big Hamiltonian which is evolving the universe. How would you know you're in a random pure state as opposed to a completely random mixed state? And for that, one measure of it is calculating the entanglement entropy of a random state versus the entanglement entropy of an infinite temperature mixed state. And Page found 3 decades ago that it is almost the same. There is less than half a unit of information to tell you whether you're in a random pure state versus the infinite temperature mixed state. And remember, this is even if you're as big as, for example, half the subsystem. Even, imagine you're half the size of the universe. Imagine for some reason you could do measurements on half the universe, which is unrealistic. Even if you could do that, even in that extreme case, you could almost never figure out if you were in a pure state or an infinite temperature mixed state. So there is very little information, regarding the random pure states by measurements confined to a subsystem. So clearly, if you do measurements on the full system, you'll be able to figure it out. But once you start getting to smaller, even half the system size, it quickly becomes extremely hard to figure out if you're in a pure state. But we will show later that constraint systems will actually violate this inequality, and constraint systems. So somehow Page's inequality is violated in constraint systems. Okay, so let's end our detour and come back to our original question. What is the structure of entanglement of typical states in isolated constraint systems? So remember, our main object here is the psi I alpha. So at t equal to 0, it is a nice, highly structured matrix. At t equal to infinity, somewhere in the middle of the spectrum, it's effectively a totally random matrix. Now, if you're in a constraint system at t equal to infinity, so you still have some randomness, but you have some structure to it. So most part of it is random, but you have some additional structure on it because some states are totally disallowed. So and now you have to ask, what does the entanglement spectrum of these kind of random matrices with structure look like? So to impose structure onto this random matrix, first we need to know how do we parameterize a general constraint Hilbert space. So how do we go from saying that, for example, there is no up on a given state to actually converting that into a general parametrization, which you can apply into the wave function. So broadly speaking, any constraint Hilbert spaces can be parameterized by 2 things. So if you consider a bipartition now, and if you consider a set of quantum numbers L for the left half of the subsystem and R for the right half of the subsystem, and then there is if N is how the system grows, and DL is a relative dimension, then constraints can impose that certain combinations of your quantum numbers are disallowed. So you can think of a general matrix, matrix C, which is 1 if it's allowed, and if it's 0 if it's disallowed. So some quantum numbers across these 2 subsystems are disallowed. And in addition to that, you need another matrix or another vector D to tell you what is the relative dimension of your different Hilbert spaces. So you need to know what is allowed and disallowed, and how fast is the Hilbert space growing. So just to make this a little more concrete, let's look at the blockaded chain again. So the blockaded chain, if you remember, is no up on neighboring sites. So now if you keep adding, now you can ask this question: I have a chain of size L, and I add an additional spin onto the end and ask how does the Hilbert space grow? Now, if you're in a completely unconstrained system, if it was a 2-level system, your Hilbert space just doubles because you have up and down. But clearly in a constrained system, not all states are allowed. For example, if the end spin was up, then you cannot have the spin you're adding in cannot be a state up. So there is some there is some lowering of the maximum to doubling of the Hilbert space in this case. So you can label the sectors different sectors of a Hilbert space. So you can split up the Hilbert space into different sectors labeled by what is the end spin. If the end spin is 0 or if the end spin is 1, in this case, it's a 2-level system. And you'll see that the Hilbert space grows in different ways. Because if your end spin was up and the only thing you can do is add in a down spin, you cannot add an up spin. So it doesn't really change much. But if it is your end spin was down, you can add either an up or a down. So your Hilbert space grows in different way depending on what was your end spin. And in the blockaded chain, the relative dimension of your two Hilbert spaces is given by phi and 1, where phi here is the golden mean. So this is why the Rydberg chain is also called the Fibonacci chain in some contexts, as I've talked about before, that the Hilbert space of pin Fibonacci anions and the Rydberg chain are the same. And this is because the Hilbert space grows like a Fibonacci sequence. So the relative dimension of the Hilbert space is given by a Fibonacci number here, the golden ratio. And now we will always look at the thermodynamic limit and ask what happens. So just to formalize the last 2 slides, in a blockaded chain, if your filled state is up and your empty state is down, then and you have a bipartition over here, like all states except states where where you have up and up on the L and up in the rest of the system. But if you're looking only across the cut, you cannot allow for L and R to be up and up. And just for notation, as I said, I've always used I for the left half of the system and alpha for the right half of the system. So your constraint matrix is given by is a 2x2 matrix because L and R can be 0 and 1 and 0 and 1. So you have 1, 1, 1, 0, with the 0 telling you that you cannot have L and R be up and up. And your relative Hilbert space dimension is phi and 1. So if this seems confusing, all I want you to take away from this is that given a general constraint system, there are these two, there's a matrix and a vector, which will tell you in general what are the constraints in the system. And you can encode even global constraints, different sorts of local constraints in these sort of matrices here. And this notation will be useful in what follows. So let's warm up with a calculation at infinite temperature. Let's ask for what is the infinite temperature mixed state. So the infinite temperature mixed state is usually boring. So because you're even though there's a e to the minus beta h, once you take temperature to infinity, that's just an identity matrix. And even if you trace it out, that's effectively an identity matrix. So your infinite temperature mixed state is just usually a boring identity matrix. But with constraints, even this mixed state looks very different. So if you go ahead and do the same thing, your initial state is of course an identity, but once you do the partial trace, you'll see that there's a non-trivial ij looks like an identity matrix. So these superscripts here denote L and R. So here delta ij is an identity matrix, delta ij1 is another identity matrix. But the main point here is that the L equal to 0 sector has more weight than the L equal to 1 sector. And if you had an unconstrained system, both of them would have exactly the same weight, and you would just get a usual identity matrix. But here it's not a typical identity matrix, and constraints tell you that even the infinite temperature, the mixed state, is different. And this is useful if you disregard what is to come. We haven't talked about wave functions yet. This is already interesting in the sense that if you are a typical expectation, and for example, a periodically driven system is that it should heat to infinite temperature. But if you had a periodically driven system in a constrained Hilbert space, the thing it would eventually heat up to would actually be different. And because of the fact that you had constraints in your system. So now this is your infinite temperature mixed state, but what we're actually interested in is the wave function. What is the entanglement structure of a random wave function? So we want to compute the reduced density matrix. Now we can take advantage of the fact that these elements of the reduced density matrix are random, and we can average over the randomness. So if you take the elements of the psi to be just Gaussian random coefficients, then this is what your matrix looks like. Remember, for an unconstrained system, this just looks like a completely random matrix. But once you have in the case of a blockaded chain, you have a big zero in here an n by n block, which is just zero. So just to recap, psi has two indices, I and alpha. I denotes a left subsystem and the alpha denotes a right subsystem. So each element in here is one state in your system. But if you're only interested in what is the left L and R doing, where L is the edge spin of the left subsystem and R is the right spin of the right subsystem, then you can look at a block structure. So if the left subsystem is 0 and 0 and the right is 0, then it's allowed. And similarly, these two are allowed. But if across the cut, if your spins are up and up, then that is not allowed. So you have a big 0 in here. So now you can construct a Wick's theorem, a generalized Wick's theorem by averaging over the randomness. The fact that these are Gaussian random variables means that you can average over the randomness and you get a Wick's theorem. And now you can represent all this in a diagrammatic formalism. I apologize if this is this is a bit technical, but I will come back to the results in a few minutes. So one of the main points here is that you can construct general Feynman. So typically once you have Wick's theorem, you can start drawing diagrammatics and calculate whatever observable you want to. So in this case, it would be the reduced density matrix. But here you have constraints. So you have decorated Feynman diagrams. So you have your delta here, delta ij's are propagators. And these propagators have additional decorations in here, which tells you what is the state of the boundary spin. And then you can have vertices, to which the propagators connect to. And then you can start putting things together. For example, the previous Wick's theorem would look diagrammatically as something like this. So this has the same content as what I've written before, just in a diagrammatic notation. So now you can start to evaluate moments of rho. So at large n, it turns out that only planar diagrams contribute, as typically in what happens in large n theories. And for example, if you want to calculate trace of rho squares, you get two diagrams which are planar, which contribute at large n. But these are, as you can see, there are some decorations here. And the interesting thing is, once you write down the value, in an unconstrained system, you just get some factor of n. But in a constrained system, you get these non-trivial polynomials which depend on a relative relative dimension of Hilbert space. So here, phi would be the golden mean for the Rydberg chain, and it can, but you can also think of tuning phi to construct different systems. So this is where all the physics is. That the Marchenko-Pastur law would not have, an unconstrained system would not have these polynomials, but in a constrained system, once you start evaluating these moments, you have these interesting polynomials that start to come out. So now you can actually try to remember, our original goal is to calculate the entanglement spectrum. We're not just interested in a few moments. We want the full entanglement spectrum to see what's going on. So for that, you can get it from the resolvent, which is a Green's function defined over here. So if you're able to, an appropriate integral transform on this will give you the probability density, will give you the spectral density which you want for the entanglement spectrum. Again, I'm sorry if I'm rushing through this, but for people who have seen this before, I guess this is a little familiar.
Sid, can I ask a question here? So you're saying that you're in a way regard this phi as a variable, right, for different constraints. How general is this? Because it seemed that a few slides ago, you did presume with this relative dimension, you kind of presumed that one of them was the number one, that it wasn't growing. Like,
right.
unconstrained, for example, is not any value phi?
No. So unconstrained, remember, so you want relative, phi equal to 1 does not mean unconstrained. Actually,
Right.
phi equal to 1 is a constraint system. So, sorry, if I go back maybe here.
Right. It would mean everything is disallowed for phi equal
here. Yeah. No, it's not everything disallowed.
Oh.
It's, oh my God, sorry, here. So if you look at this is already telling you something. So if there is more weight, if you want this weight to be the same, so it's more like phi equal to infinity would be the unconstrained system.
I see.
Yeah. So phi equal to 1 is already non-trivial, and that's where the critical point is actually. So the phi equal to 1 is the thing which is the most non-trivial of all the constraint structures. And there you can construct a physical model which realizes phi equal to 1, which I'll come to later.
Wait, but can I ask you a question about a slide that you're going to pass? Well, I think maybe a few slides ago, where you had this this relative dimensions in this vector. Like,
yeah,
there's two components, vector phi and 1.
Yeah.
Right here.
Yeah.
And so here, so I'm confused here that relative dimension, in this notation, it's hard to see that phi infinity would be the unconstrained case, no? Like the way you've written down this.
Yeah, right. So, yes. So let me come to this at the end. It'll be easier to see it, and then, yeah.
Sure. Thanks.
Yeah. So, yeah. So now we want to calculate this Green's function. And so you could imagine expanding this resolvent and evaluating all the orders of all the moments of rho, which we know are planar diagrams. So the question is, can we actually sum the planar diagrams? We know they're planar diagrams, but we can't. It's not always useful because the fact that we've reduced to planar diagrams is not always completely fruitful because there's no you still have an infinite sum of them. You need to sum them up to get a Green's function. The most famous example of this is in the original introduction of planar diagrams into physics, really, by Tooft, in large N QCD. There was a reduction to planar diagrams, but it's still it is still a big question of how do you sum all these diagrams to solve the problem. So, but in this case, luckily, you can compute an exact self-energy through a Schwinger-Dyson equation. Again, I will, for people who have not seen this before, this might not be familiar, but for people who have seen a self-energy before, all that's happening here is that you can find a self-energy which sums up all your planar diagrams. You can find a recursive structure in your diagrammatics. And the interesting thing here is that because of the constraints, you get two sets of coupled equations. So you really have, so it's a 2x2 constraint matrix. So you have two sets of self-energies and two sets of Green's functions here. And here sigma are your self-energies. So these are these are really a coupled set of nonlinear equations which you need to solve. So even for this 2x2, the simple constraint structure of a 2x2 matrix, you already end up with a set of coupled nonlinear equations. And this gives you a cubic equation in this case. So for the simple case of the blockaded chain, you can try to solve this. And these are the equations you get. So you get a coupled cubic equations. Now, luckily, you can solve cubic equations. So you can find the exact solution of this. Or if you're only interested in this analysis at small z, because remember, that is where we expect things to be universal. Then if you're doing asymptotic analysis of these equations at small z, it becomes much easier to solve, and you can find how what does this Green's function do at small z. So you can go ahead and solve that. I won't bore you with the details, and I'll just come to the results. So for now, you can get the exact. So these are all exact solutions. So for phi greater than 1, it turns out that your entanglement spectrum varies with phi, but as long as phi is greater than 1, you will always have a square root divergence at origin. So, and this is something which we call we dub the Marchenko-Pastur phase, because the Marchenko-Pastur law also has the square root divergence at origin. So the entanglement spectrum in general is shifting around, but the square root divergence does not change. And the unconstrained system, ergodic phases in unconstrained systems would also lie in this Marchenko-Pastur phase. Now, if phi less than 1, the spectrum becomes gapped, and you get a density of at origin. One way of understanding this is that, remember, there is a big block of zeros in your wave function. So once the block becomes big enough, you'll have a rank constraint, which means that you cannot you will necessarily have zeros in your eigenspectrum. So that means that you'll have a zeros in your eigenspectrum and you'll gap out your spectrum. And the way this Marchenko positive phase goes to this gap phase is through a critical point. So at a critical point, this square root singularity changes to a 2/3 singularity, which is sort of very unusual. This is a fine-tuned point, but you do get a new exponent which is exactly 2/3. And the question of what does this parameter what does it mean to tune this parameter phi, I will come to in a second. So let's look at actual random matrices to. So this is an analytical calculation from the diagrammatics. We can try to verify this by looking at actual random matrices. So if you look at the integrated spectral density, which is a more well-behaved thing, and if you do a log-log plot, you see that for different values of phi equal to 1 and the golden mean, you have different slopes, and which tells you that so this is data from actually doing summing up the diagrammatics, and the bottom is actually taking a big random matrix and with a wave function of with the right constraint structure and diagonalizing it and seeing what kind of singularities do you have. So if you take a random matrix with a 0, which is a block of zeros, which is n by n, and the rest of the matrix is 2n by 2n, then you get a 2/3 singularity at origin. Now the question is, what does it mean to be universal? I've been talking about universality. I've been saying that these things are universal. So there are actually two senses in which it's universal. One is that the singularities at small Schmidt values are universal in a given entanglement phase. So you can vary your constraint structure to a large degree, but the entanglement spectrum can change and move around, but your divergence at origin is the same until you hit a critical point. And the other sense in which they're universal is that if you're given a constrained Hilbert space, you take any quantum chaotic Hamiltonian and you believe that ETH holds true, then and if you take a state in the middle of the spectrum, then that divergence at origin should have the same exponent. It should either be a half or a 2/3, depending on the kind of constraint structure you have. So it doesn't matter what your Hamiltonian is. So this is sort of telling you that to give a contrast to this, to what happens typically when you look at entanglement spectrums of 0 temperature states, of ground states, there your Hamiltonian really is important, because then your ground state gets some specific structure. But if you're looking at highly excited eigenstates, it doesn't matter what your Hamiltonian is. It only matters what your Hilbert space looks like, and what is the constraint structure of your Hilbert space. And if you believe ETH holds true, then the entanglement spectrum of all these states across Hamiltonians should be the same. So now we'll come back to the question of what does it mean to tune phi, because I've been saying, does it make any sense to tune the parameter phi? So we can actually construct 3 different models which lie in the 3 different phases we've talked about so far. So again, let's talk about a 2-level system. And the Rydberg chain is when phi is the golden mean and you have no up anywhere. This is what the original motivation for this work was. But now if phi equal to 1, this can be realized by basically saying that up is allowed everywhere else except across the cut. So you can think of it as having a strong impurity or maybe a strong interaction across the bond, which prevents up from occurring only across the cut. And this would realize a phase with phi equal to 1. And you can also construct something like an anti-Rydberg chain, where you have, it's sort of the opposite of your Rydberg chain, where you disallow the down state everywhere, except across the cut where you have no up. So yeah, it's this last state is sort of a little artificial, but just to illustrate that you can actually realize it in a model, this constraint in a model you can consider this scenario. So now you can construct local models having these three constraints.
Just a very quick, sorry,
yeah.
Very quick question. Are you aware of any translation variant constraints?
Sorry?
Are you aware of any translation invariant constraints similar to the Rydberg case? Where
translation.
Like,
I see. For phi equal to 1, you mean?
Or any of the other phi's where it's
we haven't tried. That's honest answer. This is the simplest thing you can realize. So I thought it's sort of useful. But yeah, that's it would be interesting to have a more translation invariant realization of these models. That's fair enough. So now you can actually construct you can actually construct local models and do numerics on this to see if excited eigenstates of these models do show these interesting entanglement structure. So we chose Floquet models just for convenience. You could consider Hamiltonian models too. So if you look at Floquet models, 3 different Floquet models with those 3 different constraint structures, and look at states in the middle, quasi-energy states, which are high up, then, and if you look at what does the integrated spectral density do, and you see that they do exactly what you'd expect, that the Rydberg chain shows a 0.5 because you're integrating the spectral weight, and your defect chain shows a 1/3 singularity because you're integrating a 2/3 to 1/3. So this lends evidence, again, the rest of the entanglement spectrum looks very different, but the entanglement spectrum of these eigenstates at short Schmidt values does change because of this constraint structure. Right, and finally, one of the things I want to say is that there is a violation of the page inequality, which I alluded to earlier. So the difference of the entanglement entropy between this random wave function and the appropriate infinite temperature state does exceed the page estimate of 0.5, it seems likely that generically for constraint systems you will have violations of the page inequality. So somehow the half subsystem really has more information regarding the pure global state in this constraints case. So you can't tell. It's not a much more, but you have a little more information whether you're in a pure state or not. So finally, and so that brings me to the summary. So typical or generic states in constrained Hilbert spaces really have interesting entanglement spectrum depending on the constraint structure of the Hilbert space. And even considering the simplest constraint space, you have, this gives you that the entanglement spectra fall into different entanglement phases, which are classified by the singularity of the Schmidt values at origin. So this gives you most unconstrained systems lie in this Marchenko-Pasteur phase, but you can have exotic things like a critical point with new singularities at origin. And the diagrammatic formalism which we developed with decorated Feynman diagrams could be used to solve for arbitrary constraint spaces. You just need to generalize your C and D matrices. And you get a set of coupled nonlinear equations, which are in general hard to solve. But if you're only interested in the singularity at origin, you could tackle higher constraint structures. So then some questions that automatically leads to are there other exotic singularities? Because you got a half and a 2/3. So are there a finite set of rational singularities, maybe 3/4 or only odd ratios? And also, how do we explain the universality of the entanglement phase from a field theory perspective? Because remember, when we come back to this, we're not interested in all the physics up here, but effectively our formalism tries to solve for the entire entanglement structure. But if you're only interested in what is happening at low Schmidt values, perhaps you could construct a low energy effective field theory which only reproduces the physics here, and that could tell you why these singularities seem to be quite robust across different Hamiltonians. And I think that's it.
Thank you very much. Very clear, very interesting. Let me stop the recording here.